My name is Videsh Ray, and I'm a rising sophomore in high school. I'm in USACO Gold, and today's going to be a complete search problem. This problem is rated hard on USACO Guide. Um, it's called Load Balancing. It's from the 2016 February contest, obviously the Bronze Division. Um, and yeah, okay. So yeah, you can pause and try to understand the problem. Yeah. So basically, in this problem, Farmer John has N cows, and they're on a 2D farm. So they're all at positions x1, y1, all the way to xn, yn. And n is from 1 to 100. So there's at most 100 cows. Uh, and xi's, yi's are positive odd integers at size at most b. And FJ wants to partition his field by building long fences that are either north-south or east-west. So like the equation would be like x equals a, and a would be an even integer. So if you noticed earlier, xi and yi's were odd for the cows, and the fences are always going to be even. So there's never going to be like a case where there's a cow and the fence is running on the cow. So that'll never happen because the fence's coordinates are even and cow coordinates are odd. Okay. And then similarly, he wants to also build east-west an east-west fence, which has like y equals b, and again like b is even. And so these two integers cross at a point AB, since they're like so one is north-south, one is east-west, and they're perpendicular, so they're going to intersect at a point AB. And then they're going to partition the field into four regions. Um, yeah. And then FJ wants to choose A and B so that the cows appearing in the four resulting regions are reasonably balanced, with no region containing too many cows. So basically, they want if M is the maximum number of cows appearing in one of the four regions, FJ wants to make M as small as possible, is what it's saying. And so we have to help him determine the smallest possible value for M. Um, and then for like full submission, for like a full accepted submission, B is going to be at most a million, 10 to the sixth. And B is the is as big as the coordinates are gonna get. So yeah, okay. The first line of input will be N and B, so the number of cows and how large the coordinates can get. And then the next N lines will contain the X and Y coordinates of a cow. So over here is the number of cows, and then how large the coordinates can get. And then here is the first cow, second cow, so on. And then the sample output is 2, the smallest possible value of m that we can achieve. So we can try to uh, observe this sample input. Um, so let's just say we have an x and y graph, okay? So our first cow is at 7, 3. So like 1, 2, 3, 4, 5, 6, 7. And it doesn't have to be exact or anything. We can just kind of play it like kind of close, I guess. 1, 2, 3. Actually, I could space them out further. There's not that many points. So 1, 2, 3, 4, 5, 6, and 7. And then 1, 2, 3. So the first point is over here at 7, 3. The next point is at 5, 5. So 1, 2, 3, 4, 5. No, 3, 4, 5. So like over here. Then the next one is at 9, 7. So let's extend this a little bit. And then we have an 8 and 9. Um, yeah. So then 9, 7, so 1, 2, 3, 4, 5, and then 6, 7. So at 9, 7, we have this. Then 3, 1 is right here. Then 7, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Okay, so 7, 7 is right here. Okay, and then we have 5, 3, which is right here. And then we have 9, 1, which is right here. Okay. Okay, so now how do we partition this to find m? So in this case, let's just like think about how you would do it, right? Like let's just say in this case you're just going to randomly try it, okay? Now it makes sense, like maybe you start like try like maybe somewhere in the middle will be nice. And then this is at coordinate 5, so let's try and put this at coordinate 4, like this fence. Okay, and we see these are all split into groups of 2. They're at most, like in all of the 4 regions, they're split into groups of at most 2. So we have a size 1, but the rest are size 2. So like whichever group has the max number of cows, that's the m value. So that's how like you could picture this test case at least. Um, but then when you repetitively do these like things like in the solution when you solve this problem, you're not just going to be like eyeball thing and like this over here. I said like this looked kind of in the middle, so I put it there, and same with the horizontal one. But you need to think about how would you do it, like in code or like how would you program it. So just take a second to think about it. Remember, this is a complete search problem. Um, yeah. So essentially, the idea is to brute force it, and you're basically going to try every possible fence location. So that won't mean like going through like 1 to 1 million for all of the fence locations, like because hypothetically you could have the fence location like the coordinates on the x-axis going from 1 all the way to 10 to the 6, right? And that would be the same thing for the y-axis. So you wouldn't be able to brute force all of those fence locations, because then that would be like O of um 10 to the 6th times 10 to the 6th, which is like 10 to the 12. Um, or sorry, 10 to the 6th times 10 to the 6th, and then if basically why this 10 to the 6 comes in is because for every single like north-south fence that you try, which is like x equals some point, and x could equal anything from 1 to 10 to the 6. So you have to so that's why you get a 10 to the 6 factor right there for every vertical fence, like every north-south fence, and then the same thing for all the east-south, the east-west fences. So for one north-south fence, you would try all of the east-west fences, and so basically, if you do that, then after that you also have to like at that point it's too slow because it would be 10 to 12, but even then, even once when you're brute forcing all of the fence locations, you still have to check. So basically the point is that that's way too slow and you won't get a full solve doing that. You'll get the you'll get the first 5 test cases where b is guaranteed to be at most 100, but you wouldn't get the full solve. Okay, so essentially how you think of it is this, okay? So basically, you have to think about where the possible fence locations are when you have the other cows present as well. So basically, what fence locations would actually affect things? Um, okay, so basically, what you want to do is that you want to set fence positions for every cow's like xi plus 1, yi plus 1, right? So basically, every cow's x coordinate plus 1 is a possible vertical fence, and every cow's y coordinate plus 1 is a possible horizontal fence. Okay, so I'll explain like how this works. Um, okay, so let's say you just have some points lying around, okay? Um, let's say there's like 3 coordinates over here, right? So if you place a horizontal fence over here, over here, or over here, that wouldn't change anything, right? Like this. Because they're not actually, um, like you're moving the fence up and down, but like it's not actually partitioning the cows differently because the cows in those groups are in the same groups. Like let's say it was for this vertical fence, okay, and you tried those 3 fence positions. It's not actually changing anything because whatever was in this quadrant one stayed in that quadrant. Whatever was in this quadrant stayed in this quadrant. Whatever that was in this quadrant stayed in this quadrant. Same thing for this quadrant. Okay, so it didn't actually change anything. So how we can make sure that a fence position we try changes something is that by using the cows as reference points. So obviously, like we won't know exactly how many cows are in each quadrant when we try some fence position. So the best thing we can do is make sure that the different fence positions we try at least change something. Okay? So basically, um, let's say that you have this. So let's say you try this cow's x. Okay, this cow's x plus 1. So this cow's x, if this cow is here, its x plus 1 would be like over here, okay? So compared to having like, okay, and this, let's also look at this cow's x, okay? So this cow has like this, this is at its x and this is its x plus 1, okay? So if you partition it like this over here, let's say it's for this east-west fence. So over here you'll see that there's one here. The M value is 3, okay? Because this is the largest quadrant. There's 3 cows in it. But then compared to if you do it here, now the largest now the M value is 2, right? Because basically this is how it would look. And then there's 2 over here, there's 2 here, there's 2 here. So the M value would now be 2. Now, notice that if you try any random like fence positions over here or something, over here, they won't change anything. But then the next time it changes is if you try it over here. That's because this cow right here, this cow over here, is what makes the difference, okay? So compared to when the line was over here, when it moved here, the line basically made the cow that was in this quadrant move to the quadrant over, okay? So, like if I erase the other lines, I think it would look better. Yeah, okay. So basically, you see how if you drew the line over here, then these 3 cows would be part of one quadrant. But when you have the line stepped over a little bit farther to the right, then there's only these 2 cows in this quadrant, and then there's these 2 cows in this quadrant, right? So you'll see the change, you'll notice the change happened when you went to this cow's x plus 1, okay? And this a similar thing would happen with like the east-west fences, the horizontal fences. Okay. And the reason you want to do x plus 1, like I said earlier, is like remember they made the fence positions um odd. Sorry, even. Yeah. The cow X and Y's are odd, and the fence positions have to be even. Um, and that's because you don't want the fence to run over the cows, right? Like you want the cows to be on this side or that side. You don't want them to be like on the fence. So that's why you do x plus one, y plus one, and not just x, y. Um, also, like yeah, and then the thing is, you're not like saying that the a cow's x1 xi plus 1 and yi plus 1 has to be like the combination, like so let's say you're looking at this cow over here. You're not saying that this cow's xi plus 1, which would be like that, and yi plus 1 um are the only things that this cow can contribute, right? Because basically you want to like mix and match the x and y like positions that are possible. Because like let's say this is what you do, right? This cow's xi y plus 1 makes this fence, okay? Compared to maybe if you use this cow's x plus 1, so you stay with this vertical fence, but then let's say you want to use this cow's y value, so then you have this fence. It partitions it differently, right? So you want to like mix the like x and y situations together. Um, so yeah, every cow's x plus 1 is a possible vertical fence, and every cow's y plus 1 is a possible horizontal fence, and you want to mix all those combinations together, and then you check how many cows are in each quadrant. Okay, so hopefully that was clear enough. And yeah, so simply knowing when like the fence will be guaranteed to make a change will make your problem fast enough. So now since you're only gonna be doing basically this, right? So you're gonna have up to like n horizontal fences, right? You're gonna have up to n vertical fences, so that's n squared already, O of n squared. And then for each one you want to check like the cows. So you're gonna have to go through each cow and like see which quadrant it falls in to see like the m value. So that gives you like a final time complexity of like O of n cubed. Okay, this is a huge improvement from like the um earlier like 10 to the 12 something that we were that would have been the case if we just tried every fence position without knowing if the fence position actually changes something. Yeah. So and since n is up to 100, this would be like roughly like O of 10 to the 6. So this is well within the time limit. Okay. Now we can code the problem. So I did have it coded, like I've solved the problem before. And we'll just start from scratch though. Instead of like, I feel like it's less confusing to like just code it while explaining. Instead of trying to explain what I've already written, I feel like that would make more sense, like to you guys. So yeah, okay. So, um, we have N and B as the first inputs. Now, you don't really need B, just ignore B. Uh, it just, I mean, it matters if you're going to like differentiate between the like B at most 100 and B at most a million. But if you're getting the full solve, then it doesn't really. Okay, and then uh, you want your vector of x and y's basically, right? Of for the cows. So actually you could do a pair. In C++ you have pairs. Um, if you're using like another language and you don't have a pair in your language, so like Java, I don't think has pairs. You could just use like you could use two arrays. You would have an array for your x's and you would have an array for your y's. And as long as you kept them like the x and y's at the same position, it wouldn't matter. Um, Honestly, I might just do that here. So x of n, y of n. So we're going to store x and y's, and then for LLI 0 um, so I'm pretty sure x comes first. Yeah, they're not doing anything. Yeah, it's just x, y. Okay. All right. Okay, so now uh we know what our fence positions are going to be, right? So let's just get started with our loops. Before we get started with the loops, first let's have a variable for our answer. So let's just call it m, because that's what they called it in the problem. Just initialize m to some large value, because you want to find like the minimum possible value of m. So if you set m to some large junk value, then the following potential values of m are going to be less than that. So that's why you initialize it to some large chunk value. Okay, so now uh, let's call this, let's cycle through the vertical fences first, so the x fences. So I'll call it like horizontal fence, I guess. Or should I just give it more like a descriptive name, I guess. I'll just give it a, so it's like a north-south fence. I'll do that, I guess. Makes more sense. Um, yeah. And okay, and basically why I'm doing this, like I haven't stored the positions anywhere. Basically, we already have our xi's and yi's. So, and we know that the xi plus 1 or yi plus 1 is going to give us the potential fence. Um, so yeah, okay. Next, we're going to have our east-west fence. And so I hope you see like how this gives us like all the combinations, right? So if you're going from 0 to n for the north-south fence, basically for at this position, you're gonna say like the current x for the fence is going to be x of I plus 1, okay? And then for sorry, um, the current y is going to be the y of I plus 1. And actually, you could just take that and put it here. Yeah, okay. So basically, like since it's a nested loop, for each ns value, we're going to be going through all the EW values. So for every north-south fence, we're going to be going through all the possible east-west fences. So that goes through all the combinations of fences, right? So yeah. Okay. Now we have our current like fence positions for our like north-south, and so basically CX is the horizontal fence or the vertical fence, and CY is the horizontal fence. I just named it like X and Y respectively because yeah. And then yeah, so the final part is you just have to check how many cows are actually in each quadrant. So we're gonna have one final loop. So let's call it C, I guess. C less than n C plus. And so we can fall into one of four quadrants, right? So yeah. Okay, let's label this. So initialize our quadrant values. And then what you're gonna do is, let's say, if x of I, so here, this is how I'm gonna split my quadrants. Um, I'm gonna have this be quadrant 1, have this be quadrant 2, quadrant 3, quadrant 4. Okay, so if x of I is greater than the cx value, so basically that means that it's on the right side of this vertical fence, and y of I is greater than cy, that basically means that it's above the horizontal fence, then q1 plus plus. And then otherwise, if the x of I is still greater than the, if it's less than the c of x, and y of I is still greater than the cy, so the horizontal fence, then we've gone to q2, let's say. Right? So basically the x means the x of I being less than cx means that it's on the left of the north-south fence, but it's above like the east-west fence. It's like above the east-west fence. So then that would mean we're at quadrant 2. So similarly, we just fill out the other conditions for the other quadrants. So if x of I is still less than cx and yi is less than cy, we find ourselves in quadrant 3. And then otherwise, and actually, let me just do that. So then here we can just say else quadrant 4 plus plus. Okay. Now we've done all our like quadrant updates and stuff. For like the current combination of north, south, and east, west fence. Okay, so now you'll just do n equals min between n and max of q1, q2, q3. Okay, so basically what this line is that remember that the m value for certain north, south, and east, west fence is the max number of cows for any quadrant for that specific pair of fences. And basically you want to have like the smallest m value possible. So you're just going to do the minimum between m and whatever the current m value is. And this is the current m value. Okay, so at the end of all that, you'll just print out m, and that's it. And then I'm pretty sure this problem is file input output. So yeah, okay. And I have that here. Let's just get our sample input. And then, oh yeah, right here. So balancing dot in read stdin balance dot okay. Here we can put on our file. And long max should be enough for this problem, like for the when we're initializing m, because the bounds for this problem are pretty small. Okay, that's greater than cy. Cy right here. Oh, okay. It's because yeah, that's my bad. We have x at ns and y at ew. So same thing here. I don't know how I missed that. Yeah, my bad, but it's not too bad. It's just dumb. Let's try that again. And there should be an issue after that. Oh, I forgot a colon right there. We got 7 as our output. That's weird. Should be getting 2. Okay. Okay, let's just see what the problem was. mm, oh, it's because okay, that's I don't know why I was doing that. This is gonna be x of c for all of these. Oh, there we go. Okay, that's supposed to be okay. I just mixed it up here. I put ns and ew for some reason. Uh, x of c is like the current cow. Basically, we're going through the current cows and we're comparing it to the fence positions. So yeah, having that as ns and ew, like that was wrong. Yeah, I don't know why I put that, but okay, yeah, now we got the correct output. Um, let's just try to submit it, I guess. So, okay, we're still logged in. Insert load balancing. There it is. Okay, so it should be passing all the test cases, and yeah, okay. All right. So yeah, that was load balancing. Um, that was a complete search problem. I'll be doing like videos on new topics soon. So yeah, thank you.